60 degrees, these values are constant. Is it right? For a 60 degrees, 101, that state will be remain there. And whenever 101, that will be for 60 degrees, means this V6 will remain 60 degrees at this place. V6 will remain 60 degrees because no value is changing. And whenever we go for next step will be a 1, 0, 0. 1, 0, 0 is Q1, Q6 and Q2 are on 1, 0, 0, and this state is 1, 0, 0, V1. So this V1 will be again remain. So at which instant? At this instant, our state is changed from 101 to 100. With this space vector instantly moves from V6 to V1. Is it right? A space vector is instantly moves from V6 to V1, and at V1 position, how much duration it will remain? It will remain there for the 60 degrees. And from this 100 to it is a 110. It is a 110. It will be shift at this instant. Again, instantly it shifts from the V1 to V2. So what is the meaning of this? How the space vector moves in case of 180 degrees mode of conduction. In case of 180 degrees mode of conduction, our space vector is not continuously rotating. Is it clear? In case of this two level or 180 degrees mode of 180 degrees mode of conduction or the square wave mode or 6-step mode, we have seen that this space vector V6 will remain how many duration? 60 degrees at this instant, and instantaneously it will shift from V6 to V1. Here at V1 position, it will remain for 60 degrees, and then instantly it jumps from V1 to V2, and here also it remains 60 degrees duration, and the 60 degrees duration for 50 Hz corresponds to 3.3 milliseconds. So it will stay here for 3.3 milliseconds and then instantly jumps from V2 to V3. Here again stays for 3.3 milliseconds, 60 degrees, and then jump. So our space vector is jumping from V1 to V2, V2 to V3, V3 to V4, V4 to V5, V5 to V6, and V6 to V1. And there is it will not any step, only it is having a 6 switching vectors. So is it clear how the space vector moves? How the voltage space vector moves in case of 6-step inverter or in case of 180 degrees mode of conduction? Is it clear how space vector moves? It will be it will remain stationary for how much duration? At V1 it will be a stationary for 60 degrees and instantly jump from V1 to V2, and again here stays for 3.3 millisecond. Then after 3.3 instantly it goes to V3, and there it stays for 3.3 millisecond. It is like something quartz, okay, slow quartz you can call it, clock, and similar it moves. So here what is our conclusion we can make? A space vector for 180 degrees moves in steps of the 60 degrees. Is it clear? Space vector for 180 degrees mode of conduction moves in the step of 60 degrees. It is not rotating smoothly. Am I audible?
Yes, sir.
Is it clear? And we have seen that when the space vector moves, when the space vector moves like the steps, then our output is the 6 steps. Okay, whatever you are knowing the output of 180 degrees mode of conduction phase voltage, we are having the 6 steps. Our output for phase voltage, if you just draw the waveform, particularly for phase voltage, how is our phase voltage? We are having 1/3 VDC phase voltage, 2/3 VDC, 1/3 VDC plus, then minus 1/3 VDC, 2/3 VDC minus, then this, and then this. This is our 6 steps. Is it right? When our space vector, when space vector moves in steps, when space vector moves in steps of 60 degrees, then this will be our output voltage waveform. Now my question, if space vector moves smoothly, if space vector is running at a uniform speed, let us our space vector tip is here and this is our V star and it moves smoothly. Okay, I'm not able to draw the circle here. Let us assume this is circle. Okay, so space vector moves smoothly and completes the circle. Then what will be the phase voltage waveform? When the space vector is moving something like this, when space vector is moving a constant magnitude and it is moving smoothly and continuously, okay, its magnitude is fixed, it moves at a constant speed, then what will be the type of output we'll get?
Sinusoidal.
Anybody?
Pure sinusoidal.
Pure sinusoidal. So here another, in this case, second case, our output will be a, this case our output will be a sinusoidal. Sinusoidal. Okay, so means a rotation of space vector, how the space vector rotates and how its magnitude changes, that will determine the output voltage waveform. Is it right? Uh, what will happen to the space vector magnitude, and if it is rotating in steps, then we get a six step, particularly this waveform. If the space vector, if the space vector rotates at a uniform speed, if the space vector rotates at a uniform speed, then we get a sinusoidal output. If space vector is rotating six steps, it will be remain 60 degrees at one pulse and jump from another, and then so it is not rotating smoothly, it will jump from one place to other place instantaneously, steps of 60 degrees, and at this instant it will remain the steady position. Then our output voltage waveform will be a six step output voltage waveform, it contains the harmonics. Whereas whenever our space vector moves smoothly, then our output voltage waveform will be a sinusoidal. So the how the space vector moves and how its magnitude changes, that will determine the quality of output voltage. So how the quality of output voltage depends? Quality of output voltage depends upon what is the magnitude of space vector and how it moves. If it moves smoothly, then our output will be a sinusoid. And here we have seen that in case of this six-step inverter or a bridge inverter, two-level bridge inverter, we have seen that these two states are absent. These two states are absent. Now, here we have seen that, okay, now our interest is, so whatever we discussed, okay, particularly just now we have discussed, it is represented here. So only it is having a six active space vectors. So active space vectors we represented as a V1, V2, V3, V4 up to V6. And we have shown it here, a space vector 6 V1 to V2 instantaneously, V1 to V2 instantaneously. At V2 it remains 60 degrees, and again it instantly moves from V2 to V3. At V3 it remains 60 degrees. So space vectors remain stationary for 60 degrees, and we have seen that in case of this 180 degrees mode of conduction, we don't apply these inactive states. We can't apply these. And now based on that, so here we have shown it here, what are our waveforms, VAN, VBN, VCN, how it will be changes with respect to this, and they are having a 2/3 VDC and 1/3 VDC. What are waveform we have shown it here. This will be the waveform we can obtain, and that waveform, a particularly stable, we have shown part of that. One particular switch is on, how we get the AN, BN, CN. Already we have done this exercise, is it right? This particular state, how to find out the VAN, VBN, VCN. Okay, and whenever we are having a this upper three are on, and whenever lower three are on, our output voltages will be a zero. That we are represented. And again we have, yesterday we discussed the procedure. If V1 space vector is there, 1 0 0 state is there, then what will be AN, BN and the CN. And here very important is addition of this VAN plus VBN plus VCN will be equal to 0. 2/3 VD minus 1/3 VD minus 1/3 VD, that will be equal to 0. Now space vector we are already discussed for a three-phase balanced sinusoidal supply. Our space vector magnitude we have seen yesterday. Whenever we are having the supply magnitude is Vm, we are in three voltages. Having a peak amplitude will be equal to Vm sine omega t. So when your peak amplitude is Vm, okay, sine omega t, I am writing one of phase sine omega t. Other will be a Vm sine omega t minus 120 degrees, Vm sine omega t plus 120 degrees. And for this, we find out this whatever magnitude of the this particular peak amplitude of phasor you can call a space vector magnitude. It will be 3 by 2 into Vm, and Vm is a particularly peak amplitude of phase voltage. And for a sinusoidal supply, we see that our space vector is rotating at a uniform speed. It rotates at the uniform speed. And yesterday we discussed it complete one rotation in one cycle time. For 50 Hz, it will complete one rotation. It completes one rotation in a 20 millisecond. It will complete one rotation in 20 milliseconds. So space vector is running at a frequency equal to omega. So the speed of this will be equal to omega, or we can call it will complete one rotation in a 20 millisecond time for a 50 Hz supply. And whether our space vector is rotating anti-clockwise direction or clockwise direction. So let us assume anti-clockwise it will generate a positive phase sequence, and when a space vector rotates in clockwise direction, then we get the phase sequence, another phase sequence. Anti-clockwise direction, let us have positive phase sequence, and clockwise direction we can get the negative phase sequence. So output phase sequence depends upon the rotation of the space vector. So here already again the space vector moves at uniform speed when three-phase quantity is sinusoidal we discuss. For 180 degrees also we discuss what will happen to the space vector. They will shift from one position to other position instantaneously, but stays that the six positions, and each position it will stays for a 3.3 millisecond. And magnitude of space vector determines the output voltage magnitude. Output voltage magnitude we have seen it here. Reverse way you can go. This is the magnitude of space vector, and once this magnitude of space vector is known, from that we find out the magnitude of, this is the magnitude of space vector we can call as a V star. Okay, let us assume that V star will be equal to, our expression V star will be equal to 3 by 2 Vm. 3 by 2 Vm. And how we get the magnitude of Vm? Vm will be 2 by 3 V star. Vm will be a 2 by 3. The Vm will be 2 by 3 V star. So magnitude of space vector determines the output voltage magnitude. And now here in case of space vector PWM, we are going one technique today that is called as space vector PWM, where our space vector moves with a small step angle depending upon the switching frequency. So here in case of 6 step, it is just having a 6 steps to complete one cycle of rotation. But here when we use for a PWM, in that case, it will have a rotating in a very slow steps, and that steps, at what steps it will be shifting, that will depends upon the switching frequency. Now let us go for a space vector. So here we have shown it here. This is the relationship we have discussed here now. Just this is what Vs is the a space vector. Okay, if you are having a hexagon, I will try to draw it here. Okay, so this will be our hexagon. Okay, I will just try it here. So this is the hexagon, you assume it. Okay, and particularly our Vs is the, this will be a magnitude of Vs, you can call it, and this Vs is nothing but we find out that will be equal to VDC, and VDC is the voltage applied to the inverter. VDC is applied to the inverter. So Vs is equal to VDC. So VDC equal to 3 by 2 Vm, and from that peak amplitude of phase voltage will be 2 by 3 VDC. We will just find out. Once the magnitude of space vector is known, this VDC is the magnitude of space vector, and its phase value, peak value of phase voltage will be equal to 2 by 3 VDC. A switching frequency, let us take 36 kilohertz. So how many number of switching cycles? Number of switchings per cycle. Number of number of switchings per cycle. So we are having a 36 kilohertz, and we are having a 50 hertz. So so 36,000 divided by 50. So we'll get a 720 switchings per cycle, and one cycle we complete one rotation. So our step angle will be a 0.5 degrees. Is it clear? For 36 kilohertz, in one cycle we get how many switchings or how many steps we can get? 720 steps we can get. So one step will have a 0.5 degrees. So in case of space vector PWM, the space vector moves not at an angle of 60 degrees. It moves at a step angle of 0.5 degrees. And for each step, we have to calculate the particular switching vectors. Now, how to calculate the switching vectors? We can see. Now, let us assume here. So this is our dotted. You are seeing the hexagon. So this is a V1 space vector. We have shown it. V2 is there. So we are having a V1 space vector. Its magnitude will be how much? What is the magnitude of V1 space vector? This is a 6 space vector of our switching states of the inverter. For switching states of inverter, we are having a 6 active vectors and 2 inactive vector. What is the magnitude of V1? Anybody? What is the magnitude of V1?
VDC.
Magnitude of V1 is VDC. Similarly, V2, all this V1, V2. So we have dotted is the hexagon. Is it visible? That hexagon what we are having. And now our V star. V star is the space vector corresponding to the output voltage. Is it right? Suppose I want 100. Let us assume we go reverse way. Suppose I want the peak value to be 100 volts per phase. 100 volts per phase. That will be our equal to Vm. How much I want? A peak voltage, peak phase voltage is equal to Vm. So what should be the magnitude of space vector? This V star, our phase peak voltage is 100. So what should be V star? What should be the magnitude of space vector? What is the relationship between Vm and V star?
2 by 3.
3 by 2. Is it clear? V star will be a 3 by 2 Vm. Is it clear? V star will be 3 by 2 Vm. So means here, if I want 100 volts as a peak value, 3 phase voltages, I want 100 volts as a peak value of a sinusoidal voltage, then my V star will be how much? 3 by 2 Vm. So my V star will be a 150 volt. My V star will be a 150. And let us assume that my VDC is how much? So this magnitude is how much? V star is 150. And let us, I am applying a 600 volt DC. I am applying a 600 volt DC. So how much is the V1? V1, V2, V3. If I apply 600 volt DC to the bridge inverter, so V1, V2, V3, V4, V5, V6 will be a 600 volt. And this our V star will be now 150 volt. Is it clear? Because why it is 150? We can change the magnitude by changing this. So how we control output voltage in case of space vector PWM? How we control output voltage in case of space vector PWM? We can control the output voltage in case of space vector by controlling the V star. Now if I increase the V star, if you see the bigger circle, that is the maximum possible output voltage we can obtain. This is the maximum possible output voltage we can obtain. This range particularly we can call as a linear. In the linear mode, This is the inscribing circle of hexagon. This will be inscribing circle. If you just see it here, that is the maximum V star possible in a linear range or linear region. Are you getting inscribing circle? Circle which inscribes the hexagon. That circle, and that will be the maximum magnitude we can get, particularly in relationship with this. So we are getting arbitrarily one V star value, which may be a 150 volt. Now, how to obtain this? We are having the sectors here. How many sectors? You are giving the number, the whatever area between V1 and V2 space vectors. Area between V1, this is our V1 and V2. Area between the space vectors V1 and V2 you can call as a sector 1. So we are in sector 1 is of 60 degrees. Is it right? Sector 1 is of, and if you see it here, this 60 degrees, this sector you can see it is a equilateral triangle. Is it right? It will be a equilateral triangle. All sides, this is a VDC, this is VDC, also this is VDC, and all these angles will be a 60 degree. So sector 1 we are getting this. Next is V2 and V3, a sector spanned by two voltage vectors, switching vectors, V2 and V3, that we can call as a sector 2. Similarly, V3 and V4 we can call as a sector 3. Then V4 and V5 we can call as a sector 4. Then V5 and V6 we can call as a sector 5 and sector 6. So here we just define the 6 sectors. So is it clear? How many sectors we are having? 6 sectors spanned by the 6 switching states of the active switching states of the 2-level inverter. Now here, if I want to V star output, then what options I am having? I can apply V1 for some duration. I am applying V1 is I switch on the devices Q1, Q6 and Q2. Q1, Q6 and Q2 for some duration. Then I apply V2 for some duration, and remaining time I can apply V0 and V7. So in sector 1, which switching states I can apply to make a V star at a particular angle? At a particular angle I want to get the V star. I have to obtain the V star from whom? I have to obtain the V star from 4 switching states. When it is in the sector 1, when it is our V star, and you see this is space vector V star in the sector 1, then I have to obtain this V star from 4 switching states of inverter. V star we can obtain from 4 switching states of the inverter. And what are these 4 switching states of the inverter? One is V1, one is V2, V0 and V7. This is just filling the time. We are applying V1, very short duration we apply V1, very short duration we apply V2. Depending upon the magnitude, we find out how many duration we apply V1, how many duration we apply V2, how many duration we apply V0, how many duration we can apply V7, so that I can construct or I can obtain the V star. Is it clear? For obtaining the V star, which switching states are used in a sector 1? Is it clear? For obtaining V star, yes. Is it clear?
Yes, sir, it is clear.
For getting the V star output, we have to use 4 switching states of the inverter, and the states are V1, V2, V0, V7. If you are having sector 4, our space vector is continuously moving it with respect to time. When it comes here, which states we have to apply? V4, V5, and again V0,
V5 and
V4, V5, V0, V7. V0 and V7 will be always we require in case of a space vector PWM. Whereas in sector 5, we have to apply V5, V6, V7, V0. So depending upon the sector, we have to apply the switching vectors. And now let us go for here. So whatever we have just discussed, we are listed here. So we are having a 6 sectors. Okay, we just named it as a 1, 2, 3, 4, 5, 6. We are having a 6 sectors, and when space vector is in sector 1, whatever diagram we have shown it here, in that case our space vector is in a sector 1, then which we apply, v1 we apply, v2 we apply. V1 we apply means we switch on these switches. V1, I am applying the switching state of v1 means I am turning on S1, S6 and S2. Similarly, when I apply V2 means I will turn on S1, S3 and S2. Okay. And here we apply V4 means, sorry, here we apply V0 means we apply lower 3 devices, 2, 4, 6 on. Here V7 means I apply 1, 3 and 5 devices on. Okay, so depending upon sector we on, and direction here we have shown. Let us, this is the direction for positive phase sequence of the output voltage, anti-clockwise direction. Then if space vector rotates in opposite direction, then our uh, phase sequence will be reversed. Phase sequence will be reversed. Now we are going, so this is our space vector we have shown in, this is our magnitude of space vector we want. Okay, lower than this. And this is a V1. What is the magnitude of V1? What is the magnitude of V1? Magnitude of V1 will be equal to
VDC.
V2 will be also VDC. This angle will be 60 degrees. So this is a equilateral triangle. And we are having, let us, this space vector V star makes an angle alpha with V1. We have taken the space vector is making angle alpha, and this duration it remains at this instant which switching states we can apply. So at this particular duration, it will be how much duration it will be there? It will be how much V star will be there for how many duration? It is not 60 degrees. It will be moving at a very slow steps. Is it right? 0.5 degrees I am calling it. If it is moving at a 0.5, then how many duration it will be here? 360 degrees corresponds to how much degrees? 20 millisecond time. And 0.5 degrees is how much? We find out. That much duration. He is doing very short duration here. Here, earlier we have seen that 180 degrees mode, it will be remaining 3.3 milliseconds. But here it may be remaining maybe 0.5, very small milliseconds. Okay, here. Because it is moving with a small step angle. And it completes in 20 milliseconds. It completes how many steps? 20 milliseconds, it completes 720 steps. So 20 divided by 720, that will be millisecond, very short duration it will be present. And whenever it is present, how much duration we apply V1, how much duration we apply V2, how much duration we apply V0 and V7, we can find out. And here we are assuming, here we are applying a V1, this space vector, for a time period you can call as a V1 we are applying for a period of TA, VB we are applying for TB, and this particularly V0 and V7 remaining time we apply V0 and V7. Let us consider now here we want a VA. What is meaning of VA? If you see it VA, V star resolve along V1. VA, here if you see it VA, VA is nothing but a V star. VA is nothing but a V star resolve along V1. Similarly, VB is nothing but V star resolve along V2. And now, so we can just have a triangle. Let us consider first triangle, CAD. This triangle, if you consider CAD, what is the angle? CAD will be alpha. CAD, this angle will be alpha. And ACD, ACD will be a how much? This is alpha, so it will be a 60 minus alpha. This is 120. Angle at D will be 120. The total angle will be a 60. Alpha 1 plus this angle. So the ACD, that angle will be a pi by 3 minus alpha. Now we apply a sine rule. Okay, for this particular triangle, ACD triangle, we apply the sine rule. V star. Sine rule is what? This is the side divided by sine of angle in front of it will be equal to another side divided by sine of angle of that particular side. Similarly, this divided by this. So now here V star divided by V star is this magnitude, and angle front side will be a D, angle D here, or ADC, and it is a 2 pi by 3. So V star divided by sine of 2 pi by 3, that is VA this side, and angle will be this divided by sine of pi by 3 minus alpha. And you just we are having this equation, so V star into sine of pi by 3 minus alpha, and then it will VA into sine of pi by 3. And from that we get a VA, magnitude of VA in terms of alpha, in terms of V star and the alpha. And here we get sine of 2 pi by 3, we put the value sine of 2 pi by 3. After putting this, we get a VA. So is it clear? We obtain the magnitude of VA, and this magnitude of VA depends upon alpha and the V star. Similarly, we are obtaining the value of VB. We obtain the value of VB, and for that we consider this upper triangle ACB. We consider triangle ACB. ACB, this angle will be equal to alpha, and ABC angle will be 2 pi by 3. Then again here we apply the sine rule. Again we apply the sine rule. V star, now V star divided by sine of 2 pi by 3 will be a VB divided by sine of alpha. And here sine 2 pi by 3 we put the value, and then we get the VB, the 2 square root of 3, 2 by square root of 3 V star sine alpha. So now these two slides, we have shown it, how we obtain the magnitude of VA and VB. And how to obtain the VA? VA we can obtain by applying the V1 for a short duration. V1 we can apply for a short duration. Similarly, how we obtain VB? We VB obtain by applying a V2 for TB duration. We obtain VA, magnitude VA, by applying V1 for TA duration. So now here we are going for a volt-second balance. We are going for a volt-second balance. Now here, whatever we are having a TC. Okay, so we want the waveform to be a symmetrical or quarter wave symmetry, and for that, so whatever our switching time, I will just go this way first. So this is okay, one cycle I am telling, one switching cycle. How much duration it will be? How much time period for this? A 0.5 degrees. A 0.5 degrees, and correspondingly we find out time. This will be our 1 by TS will be 1 by Fs. TS will be 1 by Fs, and this particular TS divided equally into a TC. So TC will be TS by 2. Our TC will be a TS by 2. This will be particularly for at one instant of time, at one switching angle, at one switching. Our space vector is switching at an angle of 0.5 degrees. And whatever calculations we are making, 1 minute. Hello, ये lecture में है? हाँ. So this is our TS, is the what we are having is the time period corresponding to a step type, a 0.5 degrees. So 0.5 degrees, how much time? 1 by Fs. You will get it this TS, and this TS is divided equally into 2 TC. TC plus TC, that will be equal to a TS. Okay. So now here, so we use the volt-second balance. So here V star we are consisting of, let us take this example. V star will be our space vector. It will be equal to VA plus VB. V star will be equal to VA plus VB. You are knowing VA plus VB. So this is V star will be a VA plus VB. And now we apply the, now here we go for a volt second balance. Are you doing volt second balance? Okay, we are going for a voltage multiplied by time. So V star is there for how much duration? V star is there duration for how much TC? Half time we are taken everywhere. So V star is how much duration? V star into TC. That will be equal to how much duration VA? VA will be the duration of this, VA will be duration equal to TA, and VB will be for a duration equal to TB. So, or sorry, V1 will be equal to for a duration of TA, V2 will be for a duration of TB, and V0 or V7 will be equal to T0. And now here TA plus TB plus T0. TA plus TB plus T0 will be equal to TC. So I'm writing here a total time. So TA, what is meaning of TA? How much duration we can apply V1, that will be TA. What is meaning of TB? How much duration we can apply V2. And what is the T0? T0 is the duration for which either we can apply V0 or V7. Any one we can apply. And this total, okay, TA plus TB plus T0 will be equal to how much? TC. We get this TC. So here we are applying. So here V1, how much duration we apply is a whole second balance. That is nothing but, okay, so V1 into TA plus VB into TB plus V0 or V7 into, this is a total volt second we apply for V1 volt second, how much duration we apply V2, and how much 0 we apply for a T0 period. It will be V into TC, and this TA plus TB plus T0 will be a TC. Now now we can see it here. Once we get this, now we can use this. So this TC you can take this side. So V star. Now if you multiply here, you remove it, and you multiply, divide it by TC here everywhere. Okay, you divide the TC here. You divide TC. Okay, you divide TC. You also divide for a TC, and then if you divide this TC, you will get this expression. You will get this expression. So I have to write this first expression first. Okay, volt second balance equation. After that, TC you take to the right hand side, and then you get V1 TA divided by TC plus V2 TB divided by TC plus V0 V7 T0 divided by TC. And this particular V1 into TA by TC, V1 into TA by TC is nothing but VA. Okay, this will be so this will be equal to VA. So now we get VA will be equal to V1 into TA divided by TC. Similarly, here V2, VB is nothing but, this VB is nothing but, this is our expression. What expression we are having? V2. This is our expression for VB. So once we know this expression for expression for VA is given by this, expression for VB is given V2 into TB by TC. And once you know these two expressions, from that how we get TA? TA will be equal to VA divided by V1 into TC. So we'll get this expression, how to find out the TA, VA divided by V1 into TC. Similarly, you get the TB, VB divided by V2 into TC. And V1, V2 will be equal to VDC. Once we know the TS, and TS by 2 will be TC, we calculate the TA and TB, then we get a T0. T0 is the duration for which we apply. T0 is the duration for which we apply either V0 or V7. Is it time calculation? Is it clear to you? How we calculate the times for this? How much duration we apply V1? How much duration we apply? We apply V1 for duration equal to TA. We apply V2 for a duration equal to TB. and we apply V0 or V7 for a duration equal to T0. So any question? So in which sector we are having a space vector? So the space vector resolve along two main switching state vectors, VA and VB. We find out the magnitude of that. Once we find out the magnitude of VA and VB, then you are knowing the magnitude of V1 and V2, or you are knowing the magnitude of switching state V1, V2, V3, V4, V5, V6. Once you find out the VA and VB, VA and VB will depend upon V star and alpha. VA and VB will depend upon the V star and alpha. Once you find out the VA and VB, and depending upon the switching frequency, TC will depend. So TS will be 1 by Fs. Inverter is having a specific switching frequency. So TS will be equal to 1 by Fs. So this TS is known. TS divided by 2, you will get the TC. And once TC is known, TA is known, TB is known, you find the T0. So we are getting a 3 times TA, TB and T0. How to compute the TA, TB and T0? Is it clear? How to
Yes, sir. Yes.
Yes. Now once we compute this, now for this how to apply? Now here, whatever this V0 and V7 we are having, V0 and V7, that we have to apply for a total, this particular, this particular, either we apply V0 or V7, any one we apply. But what we do, we apply V0 for T0 by 2 and we apply V7 by T0 by 2. We divide this 0 state equally. So now here, how much V0 we apply? V0 apply for how much duration? We apply V0 for
T0 by 2.
by half of that. Okay, T0 by 2 we apply V0. And how much duration we apply V7? We apply V7 for a duration equal to, again,
T0 by 2.
T0 by 2. T0 by 2. So is it clear? So now here, V1 we apply for TAP time, VB we apply for, or V2 we apply for TB time, V1 we apply for TA time, V2 we apply for TB time, V0 we apply for T0 time, and V7 we apply for T0 by 2 time. So we apply 4 switching vectors or switching states. First switching state V1, we apply the duration will be equal to TA. We apply switching state V2. How much duration we apply switching state V2? We apply switching state V2 for TB duration. How much we apply switching state V0? T0 by 2 times. How much duration we apply V7? That will be again T0 by 2. And now this we have shown it here. So now this is a phase. So let us assume that this is switching signal, upper switch on. So this will be switching signal for first leg. So this is switching signal for which device? A phase A device. What are the devices in phase A? The first leg. Is it right? Phase A means devices in the first leg. Phase A means the devices in the first leg. Phase A, it means that the devices in the first leg. Is it right? So here a switching signal, this is a phase, means which switching signals, which devices we can make it here. This is switching signal for, what is switching signal for?
S1.
And inverted will be for S4. So out of this inverted will be for S1. So we are not shown for S4. We have shown the switching signals for upper 3 devices. And once we show the switching signal for upper 3, definitely lower 3 will be also known. So this is for S1, and phase B means which device?
S3.
Phase B means we are having a S3, and phase 3 means which device we are having? S5. So this is switching signal for these 3 devices. This is switching signal for S1. This will be for S3. Okay, and this is for S5. And now we apply V0. What is meaning of V0? Means upper 3 are off, lower 3 are on. V0 means lower 3 are on. It means that upper 3, that is S1 is off, S3 is off, and S5 is off. Is it right? This is 0. Okay, what I am showing is this is a 0. Is it right? This is 0. Upper 3 are off means 0, or lower 3 are on means 0 state. Is it clear? Then what is mean by V1? V1 is 1 0 0. Is it right? Meaning of V1 is V1 we apply for TA duration. V1 we apply TA duration. TA duration we can find out. And V1 means up S1 is on, then S6 is on. Means what will happen to S3? S3 will be off. Similarly, S2 will be on, means S5 will be off. Is it clear? This will be a V1 we apply. Then what is mean by V2? What is our V2 state? V2 will be a 1 1 0. V2 will be 1 1 0. So 1 means S1 is on, V2 S1 on. Second 1 means V3 is on. Second one V3 on. And 0 means upper S5 is off. So it will be S5 is off. Now V7, what is meaning of V7? 1 1 1. V7 means 1 1 1. Means all upper 3 devices are on. So here we have seen that S1 is on, then S3 is on, and then S5 is on. Once you compute this, then we apply V7. Okay, this is a symmetry point, you can call it here. From here we are having a symmetry. So then we apply V7. Okay, V7 is what we have done just now. V7. Then we apply V2. V2 means these two are on and third is off. So we apply the V2. Okay. Then we apply the V1. V1 means only upper devices. S1 is on. Then S3 and S5 are off. And V0 means all upper S1 is off, S3 is off, and S5 is off. So we obtain the switching signals. This is we obtain a switching signal for S1, S3, S5. Okay, this will be only for just 1.5 degree duration. Then next 0.5, the values will be changed. Depending upon quadrant operation, we are getting the switching signals. So is it clear how to get the switching signal, how we apply? And here we have seen that there will be only one change at a time, not two changes. So here all are 0. So then only S1 will on. Then in that case, S1 is already on, so S2 will on. Then third case, S1 on, then S3 on, then S5 on. And then again, S5 becomes off. After that, then S3 becomes off, then S1s become off, like that. So only at each transition, here this is a transition you can call it. Here there will be only one change of state. One switch will change its state. One switch will change its state. Only one switch will turn it on or off, not two switches. So that is we have taken a symmetry so that only one switch. So here we say S1 will be on. Then after that, only S2 will be changing its state. Sorry, S3 will changing its state. Here, S5 will changing its state. So this will be our particularly switching signals for one leg of the, switching signal for the bridge inverter, two-level inverter. And this technique we can call as a space vector PWM. This is how we generate the switching signal for this. So this is what we are already discussed. Sector 2. This is a sector 2 here, which we apply V2, V3, V0, V3, V2, V7. Okay, so which sequence we can apply, that we have written it here. Sequence first we apply, so that only one change will take place. In which sector we apply V0, we apply V5, we apply. Okay, so which sequence we can apply? So there will be only one switch will be changed at a time. And this is our what we are having is the output phase voltage. So we are simulated with the help of MATLAB simulation, and this will be a phase voltage. This will be a plus VDC magnitude, minus VDC, it will be switching. We cannot identify if the waveform is shown, whether it is a sinusoidal PWM output waveform is the same as well as the space vector. Okay, you cannot clearly identify that. Okay, that will be case. And this is our line voltage. This will be a line voltage of the bridge inverter with a space vector PWM, and we are applied to a RL load, and then our current, output current of the inverter is the sinusoidal. Output current of the inverter is almost sinusoidal. It is having some, okay, switching harmonics are present, but fundamental we are having a higher value of this. Okay, so any questions? We stop here. Any doubts?
No, sir.
I think I have sent you the experiment number 3.
Yes.
Yes, and that we have to conduct, particularly make a practical on 6th Monday at 1:15 p.m. Okay, so we'll meet Monday at 1:15 p.m. to complete our third experiment. Our theory is already over. Okay, can you do 2 experiments or 1? Okay, we'll take 1 experiment. Okay, so Monday on 6th of September. So we'll complete the third experiment. Already I have sent you the file. You are having the PPTs of that. Okay, and then once you are having a PPTs and this, so we can complete the third experiment on Monday, 6th September at 1:15 p.m. So any questions? So we'll meet on Monday. So any questions? Today we
No
discuss space vector PWM. Yes, any doubts?
No, sir.
Okay, so we'll meet on Monday at 1:15. Thank you. Those recording, please send me the recording of this lecture. Okay, thank you.